All right, if you're, I get asked a lot of times, how do I write a proof? Well, the only way to get good at writing proofs is just to write proofs. It's not like differential equations where they show you something and you go and repeat whatever they've shown you, and it's not a set of computations. And it's not really something that you can watch and just know. You have to have practice, and you're pulling so many parts of your brain together to do these problems. It's what makes us really focused and patient at working out these problems. And the more you see it and the more you do it, the better you get at it. What's great about writing proofs is once you write proofs in one class and you master the art of writing proofs, it transfers to another class that you write proofs in. So it's not like you take differential equations and it's a completely different class from combinatorics. You know, those two classes are really different. But if you do well here and you master it, you'll be able to transfer that to modern algebra. So it's a great skill to have. And look at it this way: if you avoid doing it here, well, it's still, the beast will still be there. All of you have to take modern algebra, I know, or advanced calculus to get out of here. So you might as well get it over with. And the reason I'm saying this, I can actually see the number of views on the videos, because you can go look there. I'm like looking at a few days going, wow, that's a low number of views that we have. Not good. You gotta want to get out and hit those things early and make sure you can work those problems. Huh? Maybe I do. Okay, so I'm going to show you the solutions to homework problems. I generally don't show solutions to quizzes, I just post them. But I wanted to show you the solutions to the homework problems because many of you worked them, and I wanted to show you what they ended up looking like. Of course, you could have gone a different way, not use the same method. The first one was to prove that the greatest common divisor of two consecutive numbers was 1, and I think that you asked about this. How do you transfer that to an if-then statement? Well, the best way to do this is first let D be this greatest common divisor, and you're really saying if D is the greatest common divisor of two consecutive numbers, then D has to be 1. So then you have the no and the show. And these are clean proofs. You're going to see a huge difference here because you're not going to see any of the scratch work. By definition, I know that D divides N and D divides N plus 1 because it's the greatest common divisor. And therefore, there exists x's and y's that are integers. That z with the bar through it is the integers, such that n is equal to d times x and n plus 1 is d times y. Now, I also know that n plus 1 minus n is equal to 1, so I know that dy minus dx is equal to 1. And if I factor out the d to the left, since d is an integer, then that forces d to be either 1 or negative 1. But d is positive, so that forces d to be 1. So I wrote it out here.
I just want to see, when you got n plus 1 minus n equals 1, how'd you get that one?
It's just a fact, right? If you take the n plus 1.
Yeah, right.
This is not the only way to do it. In fact, right now I was thinking that I did it a different way. You could also use that linear combination theorem that says that d times x plus d times y has to be equal to 1. And then you could actually do the factoring there and show that it turns out to be 1. So you could do this a different way. So my moods change as my hair changes, so it's the same thing. Again, I won't think the same way twice. So we get that. There's my finishing statement. You always, in every sport you do, even math, you have a finishing statement, right? Basketball, you have to follow through. Tennis, you have to follow through. Everything has it, right? Math too. Finish nice. All right, this one is an if and only if. If and only if sucks because you have two proofs. It's like it makes it sound nice. If and only if, it means like it's that nice compact statement, but really it sucks because you have two proofs to do. You have first that one direction, if k and n plus k, the greatest common divisor is 1, then you have to prove k and the greatest common divisor of k and n is 1, and vice versa. If k and n, the greatest common divisor is 1, then I have to prove that the greatest common divisor of k and n plus k is equal to 1. So I'm going to prove 1 first. We usually do this symbol, actually, to indicate which direction we're proving. So we'll do this. letting the reader know we're going this way first. So if I'm going to assume that kn plus k equals 1, and I'm going to let d equal kn, just like usual. Why would I do that? Well, some of you actually did the scratch work and didn't do this, didn't let d equal kn, the greatest common divisor of kn, and all of a sudden you got the next line you're writing was 1 divides k and 1 divides n plus k. 1 divides everything, so you haven't written down anything profound that can help you. And so that's why you want to let it be a variable, and you're going to show that that variable is equal to 1. So here, my hairstyle here was the linear combination theorem. So that's the mood I was in here. So the greatest common divisor of k and n plus k equaling 1 means that by the linear combo theorem, I can write an equation down that kx plus n plus ky is equal to 1. So just simplifying that out, I get this red equation. And by definition of d being the greatest common divisor, I know that I have these k equals ds and n equals dt. These are the nuggets that you would have got in your scratch work. That's where that comes from. So substituting this into my start equation, I get this green equation at the bottom. And there's the green equation back up there. And if I just factor, same old trick, factor out the d, and then you get d times ms is equal to 1. If I let j equal the ms, then d and j are integers, and I go through the same little argument again, then d has to be 1 because it's positive. Good? Just remember what von Neumann said. You don't learn math, you just get used to it. So part of it is that you get used to it. And some of the tricks that you use here in abstract algebra, you say, I remember this trick that we did in number theory where we had two numbers equal to 1 and that forces 1. You'll remember those tricks, and you're pulling and making your database bigger and bigger, and putting those things together is the big key part. It's not like differential equations. I hate to bring that class up. Differential equations is the grind. It's the grind of all grinds. You're just grinding out one problem after the other, and you see a procedure. It's very procedural. This is not procedural. It's artistic. You're in the same boat I am. I don't know who else is in differential equations, but I feel like my brain is going, woo. I'm teaching PDEs at the graduate level. So I'm doing number theory, which is way over on the left, and then swinging all the way over to PDEs in the night. What? The differential equations? It's a grind. I don't know why, but it inspired me to go into mathematics. You would think something like number theory inspired me to drop it, and differential equations made me go into mathematics. I had it all wrong. Okay, number 11b is false. But we'll play at some time with those in an in-class assignment. They just wanted you to play around with it. I don't know if I proved the other side. I didn't prove number 2. I'll prove number 2 some other time, but it's the same kind of concept. You would assume the other part, and you would use the linear combination theorem, and you'd end up proving the other part. Number 12, prove if A divides B and C divides D, then AC divides BD. By hypothesis, in the definition of divisibility, there exist integers, blah, blah, blah. You've seen this many times, which is why I gave you those problems on the quiz. In the 2 versions, you just had to really know how to take that definition of divisibility and then piece it all together from there. So using that equation, the red boxed equation, I can multiply that by C on both sides. I would do that because my end goal has, I have on a scratch paper my end goal, which is I need an equation that has BDs and ACs involved on both sides. So I'm going to take that boxed equation and multiply both sides by a C. And then I'm going to multiply both sides of that boxed equation by a Y. The reason I want to do that is I want to take that red boxed equation and involve D's and C's on the both sides. If I multiply both sides by Y, then I'll have a CY on the left side, and I can replace it with the D. And then I'll get from there BD equals AC as I times another integer, which is what I wanted. that means that BD is a multiple of AC, which means AC divides BD. Clean proofs, polished proofs look different than the scratch work because you have no idea how they got to where they got. You just see the nice flow. That's it. As far as I know, there's only one book for advanced calculus where they show you the pieces and then they build the proof. And that's where I got this idea from. You should see the pieces and then see the proof. And if you're in advanced calculus, the book's author is Ken Ross, and it's really cheap. But what he shows you is, he doesn't show you an epsilon delta proof just verbatim. He shows you, this is our scratch work, how to get to the epsilon delta proof first, and then he shows you the proof. And you can actually read this book and get the idea of what you're supposed to do for your proofs. So it's a real good recommended book for that class. Ken Ross is the author. I hope it's not out of print. It's a really, it should be pretty cheap. No, yeah, I think it's too low a level for our advanced calc class. We used it in our math ed program as the baby advanced calc. And, but it was, again, very nice because they showed you how they got to the proof. Now, here you want to prove if C divides AB and you know that D is the greatest common divisor of C and A, then C divides DB as well. Again, clean proof, so there's no scratch work. The scratch work was on a separate piece of paper somewhere in my head. By hypothesis, in the definition of divisibility, we have that there exists an integer s such that AB is equal to CS. So I just wrote down the definition. So that's my nugget. Now by the linear combo theorem, I know that AX plus CY equals D. And I can multiply that above equation through by B. And by subbing in the boxed equation into this black formula, I get the bottom formula, CSX plus CYB is equal to DB. And I'm home free, because I factor out the C on the left, and now I've proved that DB is a multiple of C. Since DB is expressed as a multiple of C, C divides DB, that completes the proof. Okay, are there any questions about the homework? So I think with a few of you, I've been talking to you outside of class. You either have been sending me screenshots of your work or sending me pictures of your work, and I've been telling you that, you know, maybe you try this, or here, why don't you try the linear combo theorem, or sometimes I actually mark it up and send it back to you. So I think I've only heard from about 3 people. So, huh? That's fine, right? It just makes me feel popular too, you know. I don't